And now I want to tell you about DFS, or depth first search. So, raise your hand if you've seen DFS before. Okay, so most of you know DFS, so maybe there's not much to say. So, DFS is actually even simpler than BFS in some ways, but you'll see that in other ways it's actually more complex. So, a very high-level picture of DFS. Now, I'll write out more specific sort of pseudocode soon, but it's basically, it's pretty simple. It just says visit S, and then for every, sorry? I'm muted. Oh. Can you hear me now? Well, of course you can.
Yes, thank you.
Yeah, okay. Actually, I'm curious. 21 people online. How many people have watched? It's a little bit more than 21, but it's about the same. I mean, I have this, I don't know if it's a joke or a fear or what, that I'm going to come in one day and there's no one going to be here. So, but then, you know, it's webcast, so I'll have to record it. So I'm just going to speak to an empty crowd, record the lecture, and then go back. In which case, I could probably do it from home anyway. But okay. So for every U in the neighborhood of S, just do DFS of U. Right? That's, I mean, of course, I have to put in the visited, predecessor. I have to do all that stuff. But that's the overall idea, right? You just recursively visit all your neighbors. So it's actually quite simple. It's much more simple than BFS. And for understanding DFS, or for most of the application, well, not most, but for many applications of DFS, it's really directed graphs where things get interesting. So sometimes I'm just going to put a plus over here, and this just means the out neighborhood. So what this means is I only visit the out neighbors of a vertex. And if it's an undirected graph, then you're just visiting all the neighbors. Okay? So, fairly simple. Let's just do a more specific code. But just like, so we had visited and predecessor in BFS. We also have a visited and predecessor array over here, which we will use in exactly the same way. That is, when you find a vertex, you set it to be visited, and then you set a predecessor. But there's one difference here. There's a concept that we call time. And maybe this isn't something that you've seen in your typical DFS implementation. So what is time? So I'm going to think of there being a global clock that's going. So every time something happens, the clock ticks. Right? So this is like a global variable outside DFS. And what I track is for every vertex, I track when is it discovered and when does it finish. Okay, so I'm going to write this and then I'll show you the exact code. So you have predecessor, visited as before, and you also have this notion of time, which is a global variable, like a counter. And then we'll have two arrays, that is discovery, which is the discovery time. We'll have something called finish, which I'll call the finish time. And then, of course, you have, the predecessor and visited just as before. So now let me give you the code for DFS of S. So DFS S is starting from some source. So the first thing you do is you set visited of S well, that's actually like, maybe I don't even need to do that. What I'm going to do is I'm going to set the discovery time of S to be the current time, and then I increment time. I know time plus plus doesn't work in Python, but you know what I mean, right? So there's this clock. So I discovered the word. So as soon as the process for DFS S starts, I'm going to say, okay, its discovery began. So I start the time. I set the time, and then I increment the timer. Excuse me. And then what I do is, for all u in the out neighborhood of S, I do my usual. I say if visited u is false, then I set visited u to be true. I set the predecessor of u to be S. And then I just do a recursive call for DFS of u. So there's no queue here, but there's really a stack. Right? If you replace the queue in BFS with a stack, then you get DFS. And why do I say it's a stack? Because there's a recursion stack here. Right? So it's basically like, one way of thinking of it is u just gets pushed on to, they all get pushed onto a stack. Okay. And then, okay, now here's where things get a little different from BFS. When that loop ends, okay, so when will the loop end with respect to the recursive calls? Yeah?
Once all the recursive calls are finished?
All the recursive calls are finished, right? All the recursive calls and their recursive calls and everything. So that whole recursion tree finishes, and that's when you end up at step 4. So at this point, I will say the DFS has finished. So I say the finish time of S is going to be the time. And then I increment time. Yeah. Good point. So I'll just say that, so I haven't done the initialization of predecessor visited in this. Yeah.
What's the basic condition for when it's going down, when it's like going down, there's not like a return statement?
Okay, good. So there's no return statement. So tell me, how? Good. So there's no return statement here. Is the code going to break? When is it basically going to like start backtracking? Right? That's your question. Yeah, behind?
When you either have no out neighbors or all your out neighbors are visited?
When all your out neighbors are visited, there's no recursive call that's made. And so it's just going to come here, set the time, and then leave. Yeah?
Question, so is time like an actual like wall clock / timer variable, or it could be an integer counter?
It's just an integer counter. It's just an integer counter. So I'm just going to write these here, that time is initially 0, right? So because by now we've done enough of predecessor and visited, I'm not going to tell you that all of these things were like initialized before everything began. And then I call DFS of S, right? So I didn't tell you how to initialize predecessor to initialize visited, because they're done in sort of the way that you would expect, right? So if you're calling DFS of S, the first thing you would do is you would set visited of S is equal to true, and then you would get everything to run. So that's why if you want to be really careful, I'll just add a 0th step here, and I'll just say visited of S is equal to true. So technically you don't need to do that in any recursive call because it's already been set to true here. But for the very first call, you would set that. Yeah?
Just to clarify, what do you mean by out neighbors?
What do I mean by out neighbors? So if your graph is undirected, then then there is no such notion of an out neighbor. But if your graph is directed, so let's just say this is S. These are in neighbors, and these are out neighbors. So the way to think of a directed graph is that from here, you can only go on these edges. You cannot really use those edges.
So out neighbors are like nodes that are neighbors to all other nodes. They can't contact the other one.
So, I mean, since all of you understand social networks, it's like Twitter follower, followee. So S follows all those people. Right? So it means that basically S is, but then there are things that are following S. And the way we're traversing the graph, we're only going to the followers. We could also flip it around and do any one of them. But you'll see that a lot of the reasons why you use directed graphs is like that's a situation, or like dependency graphs. So I'll give you examples of that, but imagine that each of these was like a task that had to be done, and an edge from S to V, or S to U says, you have to finish S before you can finish U. You have to do S before you can do U. Like some kind of task. Does that make sense?
Yes.
Yeah. There's someone had a question in the back. Yeah.
Time variable, is it global?
Yes.
Will we start it?
No, it's global. It's a global variable. So time, discovery, finish, predecessors. All of these are global variables.
It will be something like the number of nodes.
Yeah, so it's a bit kind of, but it's doing, yes, exactly. So think of it as every time either I set a discovery or a finish, I increment the time. What is going to be very important in the applications of depth-first search is really how do the times look over the vertices. And what we'll see is that it's actually quite beautiful that just by looking at the times, you can solve lots of problems on graphs like very efficiently. Yeah.
Just to clarify, the BFS also, if it returns outputs the same shortest path tree? Like
No, good. So let's get there. Like, what is it going to output? Yeah.
I just want to confirm really quick. So in the code, in the first half of the page, is it basically looping through every like out neighbor node and like calling DFS on that?
This one?
No, it's
So, like, okay, think of this as just a very simplistic, intuitive view. I want you to really look at this. Like, this is like an implementation of this. This is like the proper implementation of that. Does that help? I mean, this is not correct because you have to have a visited, otherwise this will just keep visiting the same vertex over and over again.
that's the last of the for.
Which, this one?
Yeah. Is it just like looping through everybody?
Is this looping through all the neighbors? But maybe I'm misunderstanding your question. But I would say, I shouldn't even put that there. This is what matters. If you write DFS, then this is what you write. The thing above is kind of like the idea. Right? The idea is just saying that it's even simpler than BFS where you maintain a queue, right? It's just that you look at your neighbors and you just visit them recursively. That's it. Okay? But the output are all of these arrays. Discovery, finish, predecessor, visited. There's also this global variable time. Of course, actually, okay, so does everyone follow what's going on? So then this is a good time to ask you some questions to make sure. So we said time is initially 0. Question: what is the value of time at the end, when everything finishes? Okay? Give you your options. Is it going to be the number of visited vertices, okay, is it going to be n, which is the total number of vertices? That's the total number of vertices. Or is it 2 times the number of visited vertices? By the way, so there may be an off by 1 somewhere, but ignore the off by 1. Okay, so most of you seem to have given the right answer. There is an off by 1 here. It should be this thing minus 1. But why is it 2 times the number of visited vertices? Yeah?
Because at every vertex you do at number 2 and number 5 you do.
Exactly. So when you discover, you increment, and when you finish, you increment. And observe that for every vertex, all these discovery and finish times are different. And the reason it's actually minus 1 is because I started off at 0. So the first time is going to be 0. The last time is going to be 2 times the number of visited vertices minus 1. Right? And it's not the number of vertices because maybe there are some vertices that are not visited. And especially in a directed graph, it's more complicated, right? Because even though everything looks like it's connected, you could start somewhere and not visit everything. So for example, if your graph looked like this picture I have here, and then there are a bunch of things over here, if you start DFS over here, you'd visit all of this, but you would never visit these guys. Right? So DFS, or any kind of traversal on a directed graph, is more complicated than in an undirected graph where you just have these connected components. Okay, so, yes?
Wouldn't it be just not the minus 1 because you add, or you increment?
I add 1 at the very end?
Yeah.
You're right. Yeah, okay, so there is no off by 1. Thank you. Yeah. Yeah?
So why did we need to increment time twice during DFS?
You mean we could just do it once? We could. It's just that it's convenient now that all the times are different. Like if you did not do this increment, well then what could happen is that it's a good question. You could end up with the finish time of something being the same as the start time of something else. Right? Because let's say that DFS S made 2 recursive calls. The first one finished. Then the next one is going to start. So its discovery time, like the discovery time and finish times would be the same. It doesn't really affect anything, but it's just sort of mentally it's easier, you'll see in the proofs if you assume that all the times are just different. Okay? All right. Good question. Yeah?
You didn't have 5 when you got to the bottom of like traversing, but go back up, all of them have the same time, finish time, right?
No, because as soon as you discover, you always increment.
Yeah, but then so you get to the bottom, the first one finishes, and then like if it was like a line of nodes, you would go all the way back. Time would never get incremented again because all of them would have been in the read step, and then time would get set to the same thing for finish.
No. So maybe it's worth drawing a picture on that. So I'm just imagining. So let me just draw some graph over here, and let me take what's going to be like the end of the recursion. So some vertex. So let's say I'm going to look at some V, and let's say all of its neighbors. Wait, let me see. You're right. They would all be the same. Yeah. Okay. Forget the picture. Yeah, you're right. They would be the same. So it's just, I think, conceptually, when we always increment the time, then we'll sort of have all the times be different. Yeah.
How would the finish time be the same? Because wouldn't you discover time and finish times for each node should be unique.
No, so what happens is, okay, then it's worth drawing this example. So hang on, just give me a second. So let's just say that there's a U which points to the V, and then this is pointing to all of these. Okay, and then you had some other neighbors. And let's just say, the way this was set up, all of these already got visited by some other stuff. So like maybe there was something over here that connected to everyone, it visited all of these, and then it went there, or something like that. Now what's going to happen is that, let's say the discovery of you, so you got discovered, and let's just say that discovery time got set to be k. So the time is now going to become k plus 1, and then it's going to visit that. So then the discovery of v is going to become k plus 1. Then time becomes k plus 2. Now what's going to happen is that v is going to look, and that there's no recursive call to be made. So it's going to then set the finish time to be k plus 2. And because if we don't do this increment, then what's going to happen is that v is going to return, it's going to go back to u. And u is going to finish. So the finish of u is also going to be just k plus 2 if you didn't do this extra increment.
The if 5 wasn't there was the thing I mentioned.
Yeah, but if 5 is there, then this is going to become k plus 3. Okay, sorry. Okay, is this like, but actually okay, so you had your hand up earlier. Okay, all right. So this is actually a good example because we'll sort of come back to this picture. But I think given the questions, it seems like you're all understanding what's going on. So now in BFS, you remember that we spent a lot of time basically understanding what happens BFS from a single source. And then I spent 5 minutes saying what happens when you do BFS on the whole graph. And here it's actually going to be the opposite. We're going to spend a lot of time thinking about what happens on DFS on the whole graph. And so I'm going to write that out over here. And so maybe this will also clarify some of the things with what is a global variable. Someone, no, okay. Okay, so what is DFS on the whole graph going to look like? So we initialize all global data structures we set time to be 0, so this counter starts at 0. And then, just like BFS, we say for all S in V, if visited S is false, then you call DFS on S. Okay? And so this is basically the procedure. What is the output? The output is a DFS forest given by the predecessor array. And then you have the discovery and finish arrays of time. So, yeah? Now I want to answer this question asked earlier, which is like, so just like you have predecessors, you're also getting, in BFS you got a predecessor here. Is this a shortest path tree, or is this a shortest path forest? Like starting from DFS, are you going to get the shortest paths? Why not? You will never, right, so exactly, right? So because, so the best way to convince you is to draw a simple example of that. And I'll even do undirected graphs. Okay? So suppose you had a graph that looks like this. Okay? And you start S over here. So if you do BFS starting from S, the BFS tree, so I'm going to draw the BFS tree, is going to look like that. Right? Because what's going to happen, it's going to start at S, it's going to shove everybody into the queue, and so all of those are set to its predecessor. But in DFS, so it depends on what the labels are going to look like. But suppose the labels were like, V1, V2, and in the adjacency list, no, that should be 6. Okay. It could be the case that S's first neighbor in the adjacency list was V1. So it's going to be S, and S is going to have this child V1. So V1 gets visited, but then you call DFS V1, which is then going to call DFS V2, so on and so forth, all the way up to V6. So your tree actually ends up being a path. It is not a shortest path tree. Okay, this example is really useful because it kind of clarifies what is going on. It's essentially your idea, but in, let's say, a homework or a test, if I say, why does this not work? The way you convince me or convince anyone is to give an example and show that it doesn't work. Right? That's, instead of giving like a long-winded explanation, you have an explanation in your head, you come up with an example. Now, what is really important here is that the structure of the tree actually depends on what the labels are. Because maybe S's first neighbor in the list, it could have been something in the middle. So let's just say, for example, okay, I'm numbering these as V1 to V6 by saying that that was the first thing in the neighbor list. Right? So maybe it was V1, V2, V6, V5, V3, V4. And so then, now I'm doing, so this is the DFS over here. And now let's do DFS on S. So I'll give you a couple minutes. I want you to actually draw the tree. And I think you will understand a lot of what's going on if you were to draw the tree. And I'm going to ask you a question. How many children does S have in the DFS tree? Is it 1? Is it 2? Is it more? Okay, so I'll give you a couple minutes to answer this question. How many children does S have in the DFS tree? This is a very good question. I want you to pay attention to these examples, and I think a lot of the stuff I'm going to say later on is going to become very easy once you understand that. Okay, so what is the answer? Okay, so there's actually a little bit of disagreement on the answer. The answer is 1. There's only one child. And what is that one child? V1. It's going to have one child, V1. Okay, next question. I'll draw out the tree then. How many children does V1 have in this DFS tree? Can I say 1, 2, or is it more? How many children does V1 have in this DFS tree? So correctly, you all said that if you start from S has one child V1, right? Because DFS from S is going to, and again, the subscript, think of that as the ordering in whatever like the adjacency list is. Okay, so now what is the answer? Okay, so most of you, it's 2. Because what's going to happen, DFS, okay, so V1 gets visited. Now we're calling DFS on V1. It's going to pick for the first thing in its list, which is V2. So it's going to call DFS on V2. V2 has one neighbor V4, which has one neighbor V3. So it's going to go V4, V3. So remember, we call this, then this, then this, then this. So this call is now just going to end. So it's going to backtrack. This is going to end, backtrack, backtrack. Then it backtracks to V1. But then V1 still has an unvisited neighbor, V6. So it's going to visit V6, which is going to visit V5. So V1 is going to visit V6, V5. I actually like this example because what it says is if you do BFS, regardless of what the labels are, the tree looks the same. So in some sense, the shortest path structure of the tree, if you think about it, the shortest path information has nothing to do with the labels on the vertices. Right? I mean, if the shortest path is 4, it doesn't matter what you number the vertices. But the DFS tree seems to be a lot more susceptible to change when you change the labels. Even the BFS tree can change depending on the labels, but you'll always have shortest paths. But here, things are much more complicated. So you might ask, like, what's the use of all of this then? How do you, like, what kind of information are you actually getting from the tree? Okay? And that's exactly where the times are now going to occur. Okay, any questions about this? Raise your hand if you've already seen this stuff with times in DFS. I think so. Fewer people. Okay, so I have things to say. Okay, so far so good? All right, so now we're going to actually understand. Okay, so these examples I'm going to keep aside. And I want to go back to understanding the discovery and finish times. Okay? Let me keep the pseudocode for DFS over here. Hopefully you can all read that. And I'm going to ask you a few questions now. So the first question, suppose DFSU is a recursive call made in DFS of S. So it's making a bunch of recursive calls. Suppose DFSU is a recursive call made, well, let me say made by. But we can also think made by and made by its recursive call, made by its, which would be made in. But anyway, it doesn't matter which one, pick any one of them that makes sense. Is the discovery time of S less than the discovery time of V? So yes, no, and maybe not. Which means that it could be or it doesn't have to be. Like it could be one way or the other. So give you a couple of minutes, unless you have a question on the question.
So
I'm sorry. Yes. You. Yes. Thank you. Thank you. That's all I'm saying. That's all I'm saying. Okay, so I think most of you are answering correctly. The answer is yes. And so why is it yes? Well, so think about this code again, right? There's a clock ticking. Which was the first call to be made? DFS-S was made before DFS-U. So its time is earlier. Okay? Clear? Is finish time of U, or finish time of S, sorry, write this clear. Finish of S less than finish of U. Again, same answers. Maybe not. Okay? Does this question make sense? Okay, so I think most of you are seeing the answer is no. And again, why? Someone want to answer why that is the question? Why that is the case? Yes?
Because the finish time is only set after S is finished recursing through all of its unvisited nodes.
Yes. Maybe even a little bit more direct way of saying that, yeah?
So if you're treating like a stack and you put S and then U on top of S, you have to finish before S comes out.
Yeah, basically, which is exactly the same reasoning, but it's even more direct, as you said. It's a recursive call. So the recursive call has to finish before the parent finishes. So that means that if DFS-U is a recursive call made by DFS-S, then you know exactly what the order of the discovery times and the order of the finish times are. Yeah? Right? And so this is not a very difficult observation to make. But again, what you will see is that these observations are going to give the power of DFS in solving problems. Okay, so I'm going to write this out. Yes?
If you go back to the, you were asking how many children there were for a certain DFS.
Yep.
Why is the answer for the first question for S1 when S is pointing to V1 to V6?
So S has neighbors V1 to V6. But the children in the DFS tree is only one. So which means that what you're looking at, if you go back to the DFS code, is what is a child? It's how many U's for which predecessor of U is set to S. Or how many V's. And there only happens to be one vertex whose predecessor is S, and that's just V1. For everybody else, their predecessor is somebody else. They're all descendants of S. That is important. They're all descendants of S, but they're not direct children.
We recognize with V6 the V1, V2 because V2 comes before.
V2 comes before, right, exactly. But what is important is that, as he pointed out earlier, it all depends on how DFS decides to explore the graph. And if it explores it in one way, it gets one structure, in another way, it gets another structure. BFS is a lot more sort of invariant to that. BFS always gives you shortest path trees. Does that answer your question?
So you're saying
Yeah? You know, you'd have to work it out and talk to me after class if this is a confusing question.
How would that look for BFS? Like if we ran BFS on that?
On this tree, you mean on this graph? In both the graphs, the BFS is going to look exactly like that. Why? Because essentially, it's going to go through all of its neighbors and push them into the queue. It doesn't make a recursive call. So everyone is just going to end up being a child, even though the ordering might be different. Because it's a shortest path tree, and that's the only shortest path tree. Yeah? Good. Okay. By the way, you know what the irony is? That, so, of course, 8 o'clock classes are bad for you. Maybe not so much for me. The reason they set it at 8 o'clock is because they could not get a classroom which was big enough to hold 140 students. But of course, 140 students aren't going to show up. So actually, we could have easily got a more reasonable time because only, about 30 people are going to show up. So go figure. And so it's kind of incredible. The amount of time, energy, and money that is spent by the staff in finding the right classroom size is huge. And I say it's a complete waste of time. It's a waste of energy because people aren't going to show up anyway. Yeah?
But if it was later in the day, would more people show up?
A few more, maybe. I don't expect more than 50% attendance even on the best of days. The only thing is it's easier to hold a midterm or that's it.
Midterm is where the size everyone does show up, right?
Yeah, but if I didn't have it, I just wouldn't hold the midterm. So it's, there's actually discussion of, okay, we need to invest in building in larger and larger classrooms. I'm like, why? No one's going to show up anyway. But anyway. Okay, so good. So what we have is this structure here. And does it also hold the other way? What does that mean? So here's my question. Suppose, and the best way to draw this is imagine this being time. Okay? And so I'll say this is the discovery time of S, and this is the finish time of S. And what does this picture say? It says this is the discovery time of U. Sorry, this is trying too small. And this is the discovery time of V. Right? Isn't that what that thing is saying? Because it said the discovery of S is less than U. No, it's V, U. Sorry, U. Finish. Darn. Finish of S, discovery of U, finish of U, and that is time. So suppose this is what the picture looks like in terms of time. Is discovery of U a recursive call made in DFS of S? So what do I mean by in? I mean that it could be an immediate recursive call or a recursive call of that, so on and so forth. Right? And again, yes, no, maybe, maybe not. Okay, so I'll give you a few minutes to think about this. It's a good time to take a break. So we'll take a break for a few minutes. When we come back, we'll discuss this. Okay. So, what? What's the answer? Okay, so there's some disagreement. The answer is yes. DFSU is a recursive call made in DFS. Why? Because again, like, yeah, go ahead. Oh, you were just reading. Huh? Yeah, so, but why? I mean, exactly. Yeah?
It's like it's the discovery of the U discovery and finish of U is a subset of the discovery S and finish of S. So it's like that can only be possible if it's made by S.
If it's made recursively, right? Because in some sense, think about the time, so the finish time is, you can think of it as like, this is really tracking how long it's on the stack, right? So what this means is that when you finished, the procedure for S is still running because it's still like on the stack. So which means that when S is running, U is running and U is finishing, which means it's basically a recursive call. That's the only way. Like everything that is running at that point is a recursive call. Yeah?
It could be maybe or maybe not.
I mean, because actually, so think about it that if indeed this is the situation. Yeah?
The finish point, doesn't it depend on how the code is structured? Like the whole, like let's say if we had this finish, okay, it doesn't make sense, but if we had this finish somewhere before the finish of U.
No, I'm saying suppose it looked like this, then this is true.
Yeah.
I'm not saying this is necessarily true. Is that clear? Actually, that was going to be my next question, but I'll still ask the question nonetheless, so that it's all written for you. Okay, so does this make clear? I'm saying suppose the times had this behavior, then actually use a recursive call for S, of like in S. That's what I'm saying. Where this is not true? Okay, but when you say this is not true, what is this? That this picture does not hold or this statement does not hold, assuming this picture?
Yeah, that the statement doesn't hold.
Assuming the picture?
Yeah.
No, it is always yes. Otherwise, I would have said maybe, maybe not. There's a lot of logical wrapping around in that statement. So maybe question?
Is there ever a situation where finish of S is before finish of U?
We'll get to that.
The difference of time from finish U to finish S is the amount of nodes that it has to go backward from finish U to discovery S.
It's a good question. So how much time? So it's both that, but it could also be like there could be some other recursive calls that are made in between.
No, but because it already finished.
You finished.
Yeah, you finish, but if you finishes, it just go back because everything is.
I'll show you an example. So suppose you had a graph that looks like this. So this is S. And this is U. So there's some graph here. But there's also some other graph here. So what happens is that S started by visiting U. So U has been discovered. U is going to do all of its stuff. It's going to finish. But then all of this also has to happen in between.
Only if the node that we are looking for is not in U.
Sure, but I'm just saying that these times it's not just backtracking from U to S, but there could be other things happening in here. So we don't know. And this is an example where other things are also happening. Okay? So I think
It is at least the time going backward. The difference.
it's at least that, but it's more, yeah, exactly. It's at least the backtracking time, but potentially more. Yeah. So I just want to be clear, like I'm not saying that this picture holds all the time. I'm saying suppose this picture holds, then DFSU is a recursive call made in DFSS. Okay, and the way you make that argument is basically you're saying that, what does this mean? It means that the procedure S on S has not yet finished at this point. It is not yet finished. So it's a parent call. So if you look at the recursion stack, you look at who are the calls that have not yet finished. Those are like all the parent calls, right, in the order of the stack. Does that sort of make sense? I mean, we can sit down and write a formal proof. I don't want to necessarily do that because of time. But as long as you get the basic idea, I think this is good enough. Because I want to use these facts to show interesting things. Yeah?
So what you're saying is that that picture is not necessarily representative of how all BFS calls would work.
Correct. But if that happens, then it looks like this. I'm getting towards making a statement of what happens in all cases, naturally. That's why I'm doing all of this here. And so at this point, I'm going to ask this question, and you should be able to hopefully answer this pretty soon. Suppose the discovery of S is less than the discovery of U. That's all I'm saying. So you have these two vertices, S and U. S was discovered first, U was discovered later. Then the finish of U is less than the finish of S. Yes, no, maybe, maybe not. Right? So I said S was discovered before U was discovered. That means that U has to finish before S is going to finish. I'll give you a few minutes, like, think about this. It's not, I mean, yeah?
Is S like the one we start at, or is it any node?
It's just any node, two nodes. By the way, in DFS S, there is no root, right? DFS of the graph, there is no root, because you call it, yeah. Yeah, okay, so what is the answer? So it is maybe, maybe not. Why? Is not the same time. You know that the times are all different. Yeah?
Because you could have just been fully after.
It could be sort of, so let me draw an example. Let me draw an example and show you. So remember, and this is where DFS gets very tricky to understand. Remember our code for DFS on the whole graph. Where is that? It's there it is. Remember we just said for all S and V we're going to do this procedure. I'm going to draw a very simple graph and an ordering on those vertices, which is going to show you this example. So let's just say your graph looked like this. Okay? But I'm going to number these vertices 1, 2, 3, 4, 5. So what's going to happen, you're going to start at 1. You're going to discover 1, which is, so I'm just going to draw time over here. So this is going to be the discovery of 1. Then you're going to discover 3. 3 is going to finish 3. Then you're going to finish 1. What happens next? You're going to discover 2. So then you discover 2. So the discovery of 2 was after the discovery of 1. But the finish of 2 is after the finish of 1. Right? So then it's actually going to finish right there. Does that make sense? Yeah?
How are you able to discover if this is directed graph?
You're going to go through all vertices in order. So it is not DFS on the source. That's why I said it's DFS on the graph, which is really important, right? So whenever I'm talking about DFS here, I'm talking about DFS on the whole graph. Right? Does this make sense? So why am I using these parentheses forms on this? It turns out there's a statement called the parentheses theorem that says that actually, if you line up time and you look at the discoveries and finishes, it forms a perfectly parenthetical string. Like if you set opening parentheses for discovery and closing parentheses, matching parentheses for finish, it will be a proper parenthetical string. Does that make sense? Right? And you start seeing why that's the case. Because if something is going to be discovered in between, it has to first finish before the parent can finish. So the parentheses theorem is basically just a consequence of using recursion. But hopefully these, yeah?
This is more related to, I guess, discovery and time.
Yeah?
You might answer this, but I'm curious what the use case of discovery time is.
Yep, I'm getting to that. Okay, yeah. So once we clear this up, I think even today I can explain it. So actually, well, I can tell you what the use case is, and then so if you compile a complex piece of code, usually you're doing you'll include different files, right? So what you do is you create a dependency graph. Like this code includes or include or import or whatever. How do you know that there isn't a loop there? If there is a loop, usually your compiler will say there is a loop. Or if there's not a loop, the compiler has to figure out the right order in which things can be compiled. Right? We're going to, basically, the way they do this is by doing DFS and using the discovery and finish times. It's the most efficient way of doing this. Okay, they set up a dependency graph with the code, and then they use these times. So that's one example. Okay, so I'm going to state a theorem here, and I call this the parentheses theorem of depth first search. I am not going to explicitly write out the proof, but by now, with all of these examples, I think the idea should be fairly clear. If you really want to read it up formally, it's there in the textbook. Yeah, question.
So for the last question.
Last question.
We were talking about the one where we went finish of S. That's applying to DFS of the whole graph.
Correct.
But if it's single source DFS, does this still hold true?
Good question. Well, okay, so I was asking you to give the answer. But anyway, no, it's still not true. It's true. This is always true. Even if you do DFS on a single source, you could imagine that all I could do is I could do this. And this is a source that I'm just going to call 0. Okay, 0 is bad because it looks like vertex. But let's say this is your S initially. And you'll see the same picture holds. Because from S, you'll first visit 1. And then you'll kind of do that. And then you'll go to 2. So one way to think about DFS on the whole graph and DFS on a source, you could imagine there being one source that just connects to everybody. So if you start DFS from that one source, it's like doing DFS on the graph. Okay? Yeah?
In that case, wouldn't it be such that the answer would be yes instead of maybe no?
No, it would still be this case. Because of S. Sorry, I meant... Okay, sorry. Don't call this S. Call this S prime. What I meant was that you're calling DFS from one source, but this happens for 2 vertices. Thank you. That was bad notation on my part. Yeah. Yeah.
So the example with the compiler and the files, could you not use BFS and some
We'll get to that. The answer is no, actually, you cannot. Yeah.
I have a question about your basic assumption of the DFS concept. Why did you leave it only for directional graphs?
No, it is true for undirected graphs as well. Everything I've said here is true whether it's directed or undirected.
But you mentioned that only for exclusively on the assumption undirected.
Oh, I see. So you can construct examples where this will also be true for directed graphs. You can do the same. Actually, a simple case, if you have a directed graph, is if you have separate connected components. If you have separate connected components, then sort of obviously this will be the case that you'll first finish the call on one and then you'll go to the other one. Yeah, good question. Okay, so let me state the parentheses theorem. The best way to sort of state this theorem is to just draw a picture. And I think that I'm just going to draw the picture and explain what the picture is. So consider any two vertices U and V. Now I'm going to denote the discovery of U and the finish of U using these parentheses, and the discovery of V and the finish of V using square parentheses. Okay? Then I'm saying only one of the following can happen. So case 1 is it looks like this. Okay? So this is V and this is U. And so in this case, V is a descendant of U in the DFS tree, or forest, I should say forest. Okay? So this is case 1. Case 2 is sort of the opposite of this picture. So U is here, V is there, and sort of V is a descendant of U. And case 3 is this, or I say technically 4 cases, but one is after the other. Yeah, question?
For case 2, should we use the descendant of V?
U is a descendant of V. Correct, thank you. And neither is a descendant, of the other. Okay, this is really messily written. I apologize. But I think what is more important is you see these pictures. So what is the case that cannot happen? So I'll just sort of... This cannot happen, which is, this is U and V. That cannot happen. Okay? So what this means is if you were to set your discovery and finish times in terms of in terms of matching parentheses, you will get a correct parenthetical string. Okay? Which is a very nice way of understanding sort of what these start times and finish times look like. Okay? You have a question? Yeah.
For case 3, you say neither is the descendant of the other. Is this, depending on the order, couldn't it be the case that one is the descendant of the other, but the descendant is evaluated first, so you get that sort of case where they're sort of separate, right? But there's still some dependence on the other.
There could be a path in the graph.
Okay.
But they're not a descendant in the DFS forest.
Yes, that
It's a good point. So there could be paths. This is only making claims about what the DFS forests look like. Okay? So just to maybe help you appreciate like why this is the case, like if you think again about homework 1, right? You have this huge graph. When you're processing the graph, your code doesn't know anything. It just has a bunch of labels of actors and just kind of processes them in some order, right? So in some sense, the structure of the graph is not something that your code directly gets its hands on when it's processing the graph. What it processes is basically alphabetical order on the actors or whatever. So it's the same thing here, right? You have like this large graph, and you're just going to process it in some order of vertices. How do you extract structure about the graph from the output? And that's what some of these, all of this is sort of getting towards. Okay. Okay, so what I'd like to do is, because I think a lot of this is getting quite abstract, I want to sort of make one more theorem. I'll just explain the theorem. We can discuss on why it's true in a next lecture. But in this lecture, in the remaining, I guess I have like 20 minutes, I want to show you an application of this so that you kind of see the kinds of things that you can do with it. Okay. So the specific, so actually forget, no more theorems about DFS. So this is the parentheses theorem of DFS, right? Okay. So I'm going to talk about a problem called topological sort and DAGs. Okay, so firstly, say consider a directed graph G equal to VE. So here's the definition. G is a DAG, which is a directed acyclic graph. If G is directed and contains no directed cycles. So what is a directed cycle? That's a directed cycle. This is not a directed cycle. In the undirected case, it's a cycle, but with direction, this is not a cycle. Right? So think of if you're basically plotting a bunch of dependencies on objects. Or even, like there are these now lots of companies that are actually building productivity tools for companies where basically like a program manager will take a bunch of tasks and say who depends on whom. Right? So think of this as like a dependency graph, right? This basically says these are various parts of your project that have to be done. And so you have to first finish this before you can finish that. So you kind of set this up as this graph and you make sure there are no loops in it. It's not like one person is waiting for code from someone else and then you keep tracing it back and they're actually waiting. And this happens actually. Someone says like, oh, that person has to write that library and then I can call it. And they'll say that person has to do it. And it kind of keeps coming back and you're like, then there's no way that this can function. And this is like, or even in processes in like operating systems, this would be like a deadlock. Like I'm waiting for this code to release some piece of data. This is waiting for some other piece of code to release some piece of data, and then they deadlock. Right? So this is, you don't want these, and a directed acyclic graph, a DAG, is a graph that is directed and contains no cycles. Is that clear? And so the problem that we often get is given the adjacency list of G, determine if G is a DAG. So what it's saying, like for every vertex I give, or for every task I give you all the dependencies. Now can you determine if there's actually a cycle in that? Okay? Is this clear? And just to give you an example of where dependency graphs come. So for example, if you have code, And I guess sort of in my world, I always think of this as C. So I say something like there's a hash include of something, right? And so this is bar.c, and maybe this is foo.c. So this is include foo.c. So what this means is that you have to first compile this before you can compile that. So you'll say, okay, now put an edge like that. And maybe something over here says include bar.c. So that means you have to first compile bar before you can compile this, so on and so forth. And your problem is if you end up with a cycle of this form, then your compiler has to throw an error. Right? Compiler has to say that the code cannot be compiled. And so there is a really beautiful solution for this problem using depth-first search. So you can actually just run one depth-first search, you look at the tree, and you can determine whether it's a DAG or not. Okay, so in DFS, using DFS, you get a linear time. This is time algorithm. By the way, so when I say linear time in graph world, I just mean it's basically O of the size of the graph, right? Just like linear time of an array. And this is super efficient because DFS is super efficient. It's a quick piece of code to write. Okay, does the problem make sense? And you see why it's not that obvious. Like you have like this huge, just like I don't know, has anyone started homework 1? You haven't? Those of you, I mean, you've probably seen that it's well, okay, maybe you've already done it, so it's not that difficult, but it can be pretty hard to kind of visualize what's going on. It's like a huge graph, right? And so when you have these really large graphs, and another thing I want to sort of emphasize is that the reason why I like teaching graphs is one is, of course, they're really interesting, but also they're one of the most powerful problem-solving tools that you have in computer science. There are lots of problems that don't look like they have graphs. Like maybe this. I mean, but when you think of it as a graph, it's like, oh yeah, it's obvious, it's just a DAG. So any situation where you have dependencies between objects, or communication between objects, or people, or entities, or whatever, there's a graph there. And then you need someone with graph theory expertise and graph algorithms expertise to do any processing. Right? So that's why it's very useful to try to think about any problem as a graph. Like, is there a graph hiding somewhere? And often you'll see in many situations there is some kind of graph problem you can construct, and then once you have the graph problem, then you try to use some of the graph algorithms to solve it. Okay. Yeah, include. So this is, okay, if that bothers you, then do import.
Oh, okay. Sorry.
Okay, do import. It's just saying that, like, you know, it's just a dependency question. Okay, so now the next thing is, suppose I give you a DAG like this. Suppose you know it's a DAG now. So you've solved the previous problem. It's a DAG. So I'll just number these 1, 4, 2, 3. Then you can imagine asking, what is a valid processing order? So what is a valid processing order for these tasks? Like if you had to do the tasks, how would you do it? Yeah?
1, 4, 2, and then 3.
You could do 1, 4, 2, 3. Could you do anything else? Yeah?
1, 2, 3, and then backtrack, then.
No, you can't. So think of these as actually dependencies. So you're not allowed to process 3 until you've finished 4.
If we apply DFS.
Don't think DFS. This is not a question. I'm just saying, suppose these are a bunch of tasks, and that arrow means it's a dependency.
Then that task can be done by using DFS.
No, it's not. So, okay, so the question is, give me an order of vertices so that edges always go from lower in the order to higher in the order. Right? So it has nothing to do with BFS or DFS. Is that? So 1, 4, 2, 3 is a valid ordering. Is there any other? Yeah? 1, 2, 4, 3 also works. But you cannot do 1, 2, 3, 4 because then there's an edge that goes back in the order. Does that answer your question? Yeah, so you see, it's not about BFS or DFS directly. It's really about the structure of this graph. Okay? So This is a problem that is called topological sort. Given a DAG G, sort the vertices in what I will call DAG order, which simply means label the vertices V1, V2 up to Vn such that for all edges E is of the form Vi, Vj, where I is less than j. Okay, so this is just a lot of wording. All it says is that you want to basically put all the vertices in order so that all edges only go in the forward direction. This should not happen. This should not happen. Does that make sense? That's what a topological order of a DAG is. Okay, so let me first ask a couple questions. The topological ordering of a DAG is unique. True, false. True, false. What is the answer? False. Why? Yeah? I just showed you an example, right? I just showed you an example. You could do 1, 4, 2, 3, or you could do 1, 2, 4, 3, right? So you could do, 1, 4, 2, 3, or you can do 1, 2, 4, 3. Did I just say 1, 2, 4, 3 over and over again? I don't know, whatever. I showed you an example, right? So the whole point of that question was, did you realize that it was an example for this? Okay, so the topological ordering of a DAG is unique. Now, there exists a graph where the topological ordering is unique. Is it true? False? It's a bit more subtle, the question. There exists a graph where the topological ordering is unique. Okay, the answer is yes, true. And what is that example? Yes, you just basically do this. Well, you could just put 2 vertices. That's it, right? So there's that graph. You could even just take 1 vertex, but sure. But you, right? Anything which looks like this, there is a topological order which is unique. And your final question for the day is, if G has a directed cycle, it does not have any topological ordering. Yes? No. If it has a directed cycle, could you construct a topological ordering of the vertices? That's true. I mean, okay, I shouldn't have done it as a double negative, but it does not have any topological ordering, right? Because if you take this, no matter how you order the vertices, you'll always have something going back because there's a cycle, a directed cycle, right? So if you look at this, there is no way you could sort the 4 vertices and not have an edge going back, right? No matter how you put it, there's going to be one edge that's going to go back. Does that make sense? Yeah? Yes? No? I think the caffeine is wearing off, I can tell. Yeah, okay. Let's end 5 minutes early then, right? Okay, so I'll just, write one last thing and then you'll be done. So the last is the problem is given a DAG as an adjacency list. Find a topological ordering. And again, for this problem, we can use DFS and we can solve it in O of n plus n time. Okay? So in the next lecture, I'll show you how DFS can be used to solve these problems, and we'll talk a little bit about the proof. So we'll end. I have office hours, I think, in half an hour, so I might see some of you there. Okay.